Hey there, this is Jose Camacho speaking from the south of Spain in Granada. I hope you're safe and that you like this presentation. I'm going to talk about the application of multivariate analysis to interpret big data sets in the context of communication networks. This is joint work with Professor Rasmus from the University of Copenhagen in Denmark and Professor David Kotz from the Dartmouth College in the US. This is the outline for the presentation, and I will start with a little bit of motivation. Let me use this small data set to motivate the use of multivariate analysis and in particular principal component analysis for data interpretation. This dataset contains a number of alcohol consumption variables linked with health variables for a number of countries across the world. A PCA is a matrix factorization approach that splits the information in the data matrix X into a set of submatrices T, P, and E. T is the matrix of scores, and it contains information about the rows in my data, in this case the countries. P is the matrix of loadings and contains information about the distribution of the variables. And finally, E is the matrix of residuals, which hopefully does not include any significant pattern, and in case it does, it can be also visualized. But now I will focus my attention on T and P. Typically, those matrices are low-dimensional matrices, meaning that they can be visualized using scatter plots like the ones I'm showing here. And the cool thing is that scatter plots of scores and of loadings can be jointly analyzed and interpreted. So, for instance, in this dataset, we can see a pattern that starts in Italy and France and moves towards the Czech Republic. And we can link that pattern as a transition from a preference of wine to a preference for beer. And in this transition, life expectancy is closer to wine, which gives us the conclusion that wine is a better alcohol type. According to the content of the data matrix, of course. Then Russia is separated from the rest of the countries, kind of an outlying country, and we can link this separation to a preference towards liquor and more higher number, of hair diseases. So with a couple of visualizations, we can understand the main patterns in my data using PCA. This application of PCA for data interpretation, data exploration, has been widely used in areas such as chemistry or bioinformatics. And we thought it would be a good idea to try and apply it to network data. Now, network data has some inherent complexities. For instance, network data has typically a huge volume, it's very large in volume, and many times comes in disparate formats like text or in general unstructured formats. So we devised the multivariate big data analysis approach, MBDA for short, in order to extend the application of PCA to network data. MBDA was originally published in this paper, in this reference you can see 1 year ago. And it is basically a sequential application of 5 steps from parsing to deparsing. Let me walk you through these steps. The first thing we need to do is to transform the raw information, raw data, into quantitative form we can analyze with PCA. For that, we make the most of the fact that most network data comes with a timestamp, so that we can identify the time evolution in it. Then we can look for specific patterns in the data, like words or regular expressions, and we can count those patterns in terms of intervals of time. So now my rows are going to be intervals of time, like seconds, days, hours, and my columns are going to be specific regular expressions that we find in the raw data. And these, the data itself, are counts of those regular expressions in the specific intervals. If we have more than one source of information, like different sensors deployed across the network, we can gather their data and combine it in a single matrix of high dimension. And then we pass this data to PCA in order to find patterns. Now this is a score plot, meaning that the dots you see are time intervals. If we find a pattern of our interest, we can use the pre-diagnosis step in order to find the features that are related to the pattern. So at the end, in this third step, we find some rows in my data that are of my interest. And with the fourth step here, we identify the features of that created the pattern of interest. So at the end, I can focus my attention in a reduced number of data points. In the last step of the method, we call the deparsing. We use the time information of the pattern and the features specific that we found to extract the specific records related to the anomaly in order to present this information to the network analyst. Now let me walk you through the case study we presented in the paper. We used a 7-year capture of SNMP traps in a Wi-Fi network at the Dartmouth College in the US. This is how the traps look like. These are SNMP traps partially translated to labels, and we have a total of 2,500 days with around 5 billion traps and 7 terabytes of data. It became clear very soon that we could not apply MBDA directly to this dataset. And the reason for that is that in the original MBDA publication, we assume that the definition of the features was known a priori. Features need to be representative of the content in the data. Otherwise, the visualization with PCA is not going to be useful. It's not going to be meaningful at all. But in a dataset like this one, which is huge with 5 billion observations, we don't know anything about the content. And we cannot get a full understanding of the content by looking at a reduced amount of those pieces of information. So we came up to the solution of building a new learning module within the parsing step that will be consistent with PCA so that we could apply it to this problem. This contribution, this learning module, is explained in detail in the paper. Now, with this new learning module, we applied an extended version of MBDA over the data. And also for the first time, we applied MBDA over parallel hardware, a cluster of computers. So the first 3 steps and the last one, which corresponds to the processing of raw data, were applied over this cluster of computers in Python, and the analysis and the pre-diagnosis were done in the regular computer using MATLAB Toolbox. Both the Python code and the MATLAB Toolbox are available online in GitHub. Now let me walk you through the different steps in the case study. First, we learn the most common regular expression that you can see in the table in order of presence, and a total of 92 features came as a result of this learning procedure. Now, in the step of parsing, we can use the features that we learn to transform the raw information into the parsed information. We did this in terms of days, but other time intervals could be used, like weeks or hours. In this case, if we use the days as the rows, the features as the columns, we transform the 7 terabytes into 1 megabyte of data that you can easily visualize in a regular computer. Provided that the learning is done properly, the visualization is going to be meaningful and representative of the data content, and therefore this transformation, this compression is really powerful. Now, because there is only one source of data, we didn't need the second step, the fusion. Now that we have a data matrix with compressed information, we can visualize it using PCA in a regular computer. And in this case, we will visualize the first 4 components. I will start with visualization for component 1 versus component 2. Recall that scores are representing the days, the rows in my original data, and loadings are representing the features that we learned in the first stage. And both plots can be interpreted jointly. Now then, at my left, I have a visualization of the days. Each dot is a day, and we use colors in terms of the years. And in the visualization at the right, the features that we learn are represented by red dots. And we also added a shadow of the scores in order to simplify the interpretation. There are 2 main patterns in this visualization. First, we have a pattern from low activity towards a higher activity. And this represents in the days a transition from holidays to busier periods of the year. Then we can also see that the different years are evolving in different directions, and we can link each of these years to different regular expressions. This means that basically the trap content changed across the years, and this observation was validated by the network analyst. Finally, we also found a pattern, this cluster here, which contained a number of observations in 2018, which, when we investigated it, we found that it was representing the transition to a duogram of this network. So main patterns in the network, main changes are reflected in the plots. Now let us end up with the third and the fourth components. We can again visualize as a scatter plot of scores and loadings. And in this case, we again see the duogram deviation, the duogram cluster, and 2 additional deviations, one in 2013 and another one in 2017, which we would like to analyze in more detail. For that, we go to the 4th step, the pre-diagnosis, in which we can find the patterns, the features that were connected to this deviation. So for the first deviation here, we found that these were the patterns, the features, which represent authentication failure. So we have a first diagnosis of the problem. There were a high number of authentication failures in the access points. And then we have the second deviation, which corresponded to a high number of restarts in the access points. We can see the traps for going up and going down of the access points. If we need further detail of those anomalies, we can map them into the raw information, and we found that the first anomaly was connected to more than 5 million traps, while the second one was connected to 19 million traps. We can gather into a data file and send them to the network analyst. If you want to know more about this analysis, you can access an extended version of the paper in arXiv. Now, as concluding remarks, takeaway messages is that PCA is an interesting tool for data exploration. MBDA is an approach to extend this exploration through PCA for network data. In this paper, we introduced a feature learning approach to MBDA, and we illustrated this application in a real big data set with more than 5 million records. Thank you very much for listening.